Thank you very much. I'm really happy to be speaking here. I would like to talk about rational points, zero cycles, and norm principles. I gave some part of this talk in CMI maybe 2 years ago, and this is I hope to recap what we did, and also maybe tell you some more about the recent progress on this question. Okay, so I thought I will start with some generalities. Just bring in some poetry. So here is the famous, probably fake epitaph of Diophantus, which is trying to tell you how to calculate his age when he died, right? So this is the linear equation: x is x by 6 plus x by 12 plus x by 7 plus 5 plus x by 2 plus 4. For those of you who know this, these two lines have been modified for poetic license. Anyway, so you're trying to solve a linear equation, right? And the answer is 84. Then you move. So maybe if you go to Bhaskhar's Leelavati, and then you tell your friend, if all the three sides of a right triangle are unknown, then can you tell me the values quickly? He actually gives a parameterization for creating Pythagorean triplets here. But anyway, you're trying to find solutions to x squared plus y squared equal to z squared. And there's a more poetic description where you have a peacock trying to eat a snake, right? That's how the Pythagorean triplets come in the picture. Or there's also a lotus in a pond, and you're trying to measure the depth of the pond and things like that. But anyway, at the end of the day, you're trying to find solutions to x squared plus y squared is z squared. And then again, you have the famous x power n is y plus y power n is z power n, where n is at least 3. So this is the margin note from Fermat's copy of Diophantus Arithmetica. Okay, and you observe that there are not too many solutions to this equation. Okay, so maybe basically we can say some part of algebra has been trying to figure out. So you have a field, you have a polynomial ring and n variables, you have a bunch of finite set of polynomials, and you're trying to find common solutions to them, right? So if you have a field extension L over K, then this is what the set of common solutions is, just n tuples which solve all the equations. And then, right, so this is the base question, right? Is there a common solutions for the polynomials over K? Okay, so now just translating it to more geometric language. So again, I'm being a little imprecise here, but supposing you have a field of affine variety, because it has a topology and everything, but basically you have systems of linear equations and you have solutions to them. And it's defined over a field. So if you have an extension L over K, then I call an L point to be any common solution to these guys, right? So x of L denotes all L solutions to these set of equations. And what do I mean by rational points in the title? I mean the set of K points, right? So I'm talking about the solutions over the base field. Okay, so this is rational points in the title. So now the question now becomes, you're given a affine variety x, is there a rational point of x? Okay, so let me try to give you a running example to keep in mind. So here is a real circle, so you're working over the reals. You have x squared plus y squared equal to 1. What's a real point? 1, 0 solves this equation. Here's another complex point, hopefully root 2i solves also the equation, right? So you have lots of complex points, lots of real points, etc. Now let me slightly twist the equation. Right? So instead of x squared plus y squared equal to 1, let me look at x squared plus y squared is minus 1 over the reals. Now this guy does not have any real solutions, but of course you have complex solutions. Okay. So this has no rational points, that's the point. Okay, then now, of course, establishing, going back to algebra, so given a variety, so you have the associated coordinate ring with it. So it's the polynomial equations modded out by the ideal defining it. Points of x are precisely prime ideals. Close points, I mean the maximal ideals. And every close point you've got a residue field, right? It's basically got by the polynomial mod the maximal ideal. So you have a residual field extension associated with each close point. Okay, and I need this to define the next thing in the title. Okay, so maybe an example would be good. So x squared plus y squared is minus 1. You have this ring Rxy by x squared plus y squared plus 1. Close point 0i, of course, corresponds to x y squared plus 1. This is a complex point, right? So it's the residue field is C. Okay. Okay, so now let me talk about what a zero cycle is. So you're given a variety over K. What is a zero cycle? Is just any element of the free abelian group of the closed points. So you can take any integral, finite integral combination of the closed points. What is the degree of the zero cycle? So it's basically you are summing the coefficients but with weights attached to it, right? You're weighting it by the residue field degree extension. So again, maybe an example would be good. So let's have the running example in mind. So you have the circle. So let's look at some zero cycles. So maybe it's -5 copies of 1 0 and 3 copies of root 2 comma I. What is the degree? It's -5, but this is a real point, so its weight is 1. This is a complex point, its weight is 2, right? So you get a zero cycle of degree 1. If you twist the example, so let's say you take -3 copies of 1 0, 1 copy of 0 I, you can calculate its degree is going to be -4, right? And of course you can now try to see how can you come up with a zero cycle of degree 1 in this example. Okay, so here is the base question, right? So you have a variety. Of course, if I just have a rational point, right, it's defined, you just take one copy of a k rational point, so that is a zero cycle of degree 1. Okay, so is the converse true? So the big question is, if you have a variety, supposing you know that it has a zero cycle of degree 1, do you have a k rational point? And again, in the running example, it's perfectly set up because, you know, in the real circle, we produced a zero cycle of degree 1. Of course, there are lots of real points, so you do have lots of rational points. In the twisted example, it's not hard to convince yourself that there is no zero cycle of degree 1 and there is also no real point. Okay, well, what about more examples? So you can talk about maybe genus 1 smooth projective curves. This is going to be a simple application of Riemann-Roch, okay, because if you have a divisor and then you compute, you may find an effective divisor, okay, so it will have, that will exactly be a degree, a rational point. But then if you move to maybe genus 2 curves or more over finite fields, right, you have what are called Weyl bounds. So basically you can find lots of points and then, you know, you can play around and get a GCD of 1, okay, but you need not have a rational point. So you do have examples and you do have non-examples. Okay, so clearly this question is too broad. If you just ask for a general variety, you ask this question, it's too hard to expect a positive answer. So you restrict your class of varieties to what are called principal homogeneous spaces over the field under linear algebraic groups. Right, so here's a bunch of more terms. So let me try to define what these are. Okay, linear algebraic groups. So you have a field. So a linear algebraic group is just an affine variety which is also a group compatibly, right? So your group operations must respect the Zariski topology and everything. Or if you like, you can think about it as a closed subgroup of GLN. Again, maybe examples are better. So, you know, you have lots of very well studied groups. So you have the special linear group, so matrix groups with determinant 1, special orthogonal group, so again determinant 1 but they preserve a quadratic form. You have symplectic groups, then you have special linear groups, etc., etc. Okay, so just in mind, what is the example that I gave you? It was a torus, right? So you have this. The equation was g squared plus a squared is 1. So how is this a group? So just think about it as gh as g plus ih, right? So this is basically norm 1 if you define the norm as x squared plus y squared, right? And the group structure is exactly how you would multiply complex numbers. So this is a real torus. Okay, now what is a principal homogeneous space? You have a base field, you have a separable closure, and what is my variety? It's a nice variety in the sense you have a G action, right? The group acts on this variety, but the action itself is nice in the sense when you go all the way to the separable closure, that action should just look like G acting on itself by translation, right? So it's a nice variety with a nice action when you go all the way up to the separable closure. In this case, if you just like to think about the points, so if you look at the separable points of the group, it will act what is called simply transitively on the separable points of the variety. Simply transitive just means it's a transitive action and there are no stabilizers, right? All the stabilizers are trivial. So if you give me 2 points in your variety, 2 k separable points, there is exactly one group element which moves one to the other. Okay, so at the separable closure, it's a really simple action to understand. And of course, this example was set up so that it is a principal homogeneous space, right? So you've got this circle, g squared plus a squared is 1. You've got this variety which is twisted, right? It's x squared plus y squared is -1. Again, think of the tuple gh as g plus ih, xy as x plus iy. The norms are 1 and minus 1 and they multiply, right? So 1 times minus 1 is minus 1. So this acts, the group, the circle acts on this affine variety, and it is in fact a nice action. It is a principal homogeneous space. So I've basically produced one example of a principal homogeneous space under a linear algebraic group which answers that question positively. So you have a zero cycle of degree 1, you also have rational points. And this is precisely the question of Serre. So this was posed in maybe 1962. So if you have a connected linear algebraic group over a field, you have this very nice variety. So it's a principal homogeneous space under the group over the field. If you have a zero cycle of degree 1 on your variety, do you also have a rational point? And because it's a question of Serre, maybe you should carefully investigate whether all these are, I mean, why are you restricting yourself to such a particular, variety? So, all the things are kind of essential. So note, I've imposed the fact that G is connected, and in fact G is connected is essential. So if you have, there are counter examples even for finite groups. You can realize it as maybe Galois groups of number fields or something. And then, so you have this example, I think was given by Serre himself, or maybe Philip Gilles had written it down. And then of course you can ask, well, can you make your action a little more flexible? So can you allow stabilizers, for example? So can you restrict yourself to say projective or quasi-projective homogeneous varieties? In that sense, again, people ask these questions, and there are counterexamples in both the cases, right? So you might have zero cycles of degree 1, but you might not have a rational point. And these examples were written down by Parimala for the projective homogeneous variety case, and for the quasi-projective, I think it was by Matthew Florence. So it turns out that this question is exactly phrased for exactly the right kind of varieties and for the right kind of linear algebraic groups. Okay, so now how do you go about solving this question? So how do you find the rational point? So I want to translate everything back to algebra. Okay, so for a group over a field, you have this Galois cohomology set H1 kg. So this is not just a set; it's a pointed set. You have a special element which is the trivial element. And what is the connection? So every principal homogeneous space corresponds to an element in H1 kg. Up to isomorphism, the principal homogeneous space, and this is up to, this is the element. Okay, so what is the dictionary from the geometric side to the algebraic side? So supposing the principal homogeneous space is X, the class of X, it corresponds to this element. So this guy has a rational point precisely when this is the trivial element, right? So the question really asks whether you're basically looking at a set and you're checking whether some element is trivial or not in the algebraic sense. What is the other dictionary? So what does a zero cycle of degree 1 correspond to? It basically says, see, xi is a closed point. It precisely means x gets a point when you go to that field extension, right? So therefore, this zero cycle of degree 1 exactly means that you have this this element, and it becomes trivial over a bunch of co-prime degree extensions. So in algebraic language, what is the question? So the question is, you've got a connected linear algebraic group, you've got a bunch of finite field extensions, all of them have some degrees, and the GCD is 1. And then you have this Galois cohomology exact sequence, H1 kg, which sits inside, it has a map to H1 Lig. You have an element here, it becomes trivial in every one of these coordinates, so is it trivial to start with, right? So this becomes a question about kernels. So is the kernel trivial? Okay. Any questions so far? Okay. Okay, so this is a very well studied question in the sense you already know some answers for some well studied groups. So for example, if you take PGLN, this is the projective general linear algebraic group. This Galois cohomology set classifies what are called twisted forms of matrix algebras up to isomorphism. What do I mean by twisted forms? You take some algebra, when you go all the way up to the algebraic closure, it just becomes a matrix algebra. Okay? And these are what are called central simple algebras. And this is a fact from the theory of central simple algebras, that if you have a guy which becomes untwisted after co-prime degree extensions, it's already a matrix to start with. Okay? So you know the answer for PGLN. Here's one more nice example. So you have a central simple algebra. What is the group? So let me define the group, which is called SL1A. So remember, this is a twisted guy, right? So when you go to the algebraic closure, it becomes a matrix algebra. Then you have the determinant map. So you have a map from A to K bar. okay, but it's easy to convince yourself that this actually lands in K. So you can think of the reduced norm as coming from this map here. So SL1A is exactly all the guys which have reduced norm 1. Okay, so this is the linear algebraic group, and just like I set up the example where I just twisted the circle by a scalar, any principal homogeneous space exactly looks like this. You take reduced norm equation, instead of 1 you just twist it by a scalar, right? And you can see that this guy will act on this guy in simply transitive. And so basically this Galois cohomology set is precisely scalars mod reduced norms. Reduced norms are the trivial ones. What is Serre's question saying? If you have a scalar, you go to co-prime degree extensions. If it becomes reduced norms, it's already a reduced norm to start with. Okay, so and again this from the theory of central symbol algebras. Okay, and there are several more very well studied examples. Let me just mention 2 of them. So this is stated for an odd extension, right? You just have an odd extension. What is Springer's theorem? It's the theorem for orthogonal groups. So this preserves the quadratic form Q, and it just tells you that if you go to an odd degree extension, then the kernel is trivial. So if you have an element, it becomes trivial after an odd degree extension. It's trivial to start with. How does this answer Serre's question? So remember, in Serre's question you had a bunch of co-prime degree extensions where the elements become trivial. So all of them cannot be even, right? One of them has to be odd. So this will answer Serre's question for that. And you can also do so Baer and Lenstra generalize this for isometry groups. So you have an algebra with an involution, and then you have this is isometric group, and you have a similar result there. Okay, so upshot is you know Serre's question for some nice classical groups. But what about the general case, right? What about a general linear algebraic group? So let me just mention some adjectives for linear algebraic groups. There are semi-simple linear algebraic groups. So instead of defining it, maybe let me just give you some examples to keep in mind. You've got simply connected ones like SLN. You have adjoint ones which are like PGLN, and you have guys in between which are neither simply connected nor adjoint. So maybe you're going SLN mods for some parts of its sector. You have another class of groups, reductive. And the point is that the reductive group is a larger class than semi-simple, right? So if you're semi-simple, you're also reductive. Okay. I should also tell you that you've got some types of groups. So you have the classical types. By that I mean A, B, C, and non-trilitarian D. You have exceptional groups, a bunch of more classes. And I need to tell you all these adjectives to state the next result. So this is the first attempt to generalize, answer Serre's question in a more general fashion. So this is a theorem by Jody Black, and she answers, so she's my academic sibling, so she's Parimala's previous student. So she takes a field of characteristic not 2. We always have this restriction because we like to work with quadratic forms and we don't like characteristic 2. Maybe we will in the future. But yeah, so you take a field of characteristic 2 and then you have a semi-simple algebraic group, okay? And she answers the question if it's classical for simply connected or adjoint, right, for the 2 ends of the spectrum. But if it's an exceptional group, she wants it to be quasi-split, which means you have a Borel defined over the base field. And of course, we don't want E8. E8 is a mystery, so you don't want E8 things there. So then Serre's question has a positive answer for this. So at least if you restrict yourself to the classical case, you have the answer for simply connected or adjoint classical groups. So obviously the next step for me is to generalize this to Serre's question for reductive groups. So this was part of my thesis. So again, you have a field of characteristic not 2, you have a connected reductive group, and if you look at the Dinkin diagram of its semi-simple part, simply connected cover, and I don't want it to have components of I want it to have components of A, B, or C. Okay, then it has a positive answer. If I want to talk about if you want exceptional groups also, then I want it to be quasi-split, and then the Dinkin diagram does not contain connected components of type E8. Okay. I just want to point out there is a D missing, whereas Jody covers A, B, C, and D. Okay, and in fact my proof uses her, so I will tell you. So I use her result and extend it.
But there's also this funny thing about either simply connected or adjoint, the two extremes.
Exactly. So she doesn't answer it. For example, my whole problem started with you have the spin groups, and then you have the PGO plus, but then you have these half spinor groups in between. So we didn't even know how to answer it for half spinor groups. So that was the whole point which I started to try to answer. But it turns out that you can just answer it for reductive groups in more generality. So, you know, even if you want to restrict yourself to semi-simple groups, you can't answer the things for the in-between groups. And so, yeah, but I also want to stress in the fact that in the classical case, there is a D missing, right? So, Jodi does have the result for type D, whereas I don't have the result for type D in this case. Okay, so let me try to illustrate how the proof sort of goes, and it will go via Jodi. So Jodi's work is essential to the proof. The proof is where it's basically like, how do you, maybe you know Serre's question for some groups, how do you build it up, right? So let's say SQ holds if I mean Serre's question has a positive answer for G. The trivial cases are abelian groups, right? This is just a diagram chase. So Serre's question holds for abelian groups. It's also not, it's easy to believe that if it holds for A, if it holds for B, it will hold for the product. Here's one more, again this is an easy diagram chase, but supposing you have a central extension of a group by a nice torus, which is called a quasi-trivial torus, right? Basically it means, what I really want is it's H1 trivial, so the H1 guys are 0. Then Serre's question holds for A exactly when it holds for B, right? So you can sort of go up from, you start with some groups, you can sort of pad up your groups by these processes. And so this is how the proof proceeds, right? So you, first of all, you're working over an arbitrary field, so you sort of move it to a characteristic 0 field, so you don't get into this imperfect business things. Once you're in this so this you do by moving lemma of Garber, Liu and Lorenzini. But once you're in characteristic 0, so you have your reductive group, you take its semi-simple part, and then you take the adjoint portion of it. So go mod its center. And by Jodi, you know this case, right? You know how to answer this. And then you sort of pad up your adjoint group, okay, using all those 3 lemmas, you know, in a nice fashion to get Serre's question for some intermediate group, G tilde. Okay, so I want to answer the question for G, but somehow I've answered this question for G tilde. What is the relation between these two guys? They are related by a short exact sequence where this is a torus, right? So 1, G, G tilde and T. But then you get stuck, right? I mean, I still want to answer it for G. How do I know it for G tilde? What do I do next? And I really got stuck, right? So, but what is mathematics is letting the principles do the work for you so that you don't have to do it for yourself, right? And this is very apt because we have what are called norm principles, and they do the job for you. Okay, so let me tell you what the norm is, and then tell you what the norm principle is. Right, what is, supposing I take a commutative linear algebraic group, take a finite separable field extension. So I can define a norm map from the L points of the commutative guy to the K points of the commutative guy by taking a point and basically running it over the Galois conjugates, appropriate Galois conjugates. This is exactly like how you would, so for example, if you just work with T as Gn, and let's say you're working with complex numbers to real numbers, this is your precise norm, right? So you have x plus iy, and then you're going to send it to x plus iy times x minus iy, so it'll go to x squared plus y squared. And it coincides with the usual field norm whenever you have L over K, even if it's not Galois. This is the usual norm map. And the point is, it's only well defined because T is commutative. If T is not commutative, order matters, right? So this is not well defined. Okay. So I have a norm map. What is the norm principle for me? So I've got a linear algebraic group, a map to a commutative linear algebraic group, and all this is defined over the small k. I have a field extension L over K. Okay, so I can now define this partial square. So I can start with G of L, go to T of L, go down by the norm map, but then I can start with G of K and go to T of K, right? So what is the norm principle question? We say that the norm principle holds if you start here and go all the way down, then you also come from here, right? So norm of the image is contained inside the image. So we say that the norm principle holds when the norm of the image is contained inside the image. Yeah, okay, so again, remember Serre's question was ultimately a question about kernels, right? And norm principle is about images, and now you begin to see why it works, right? Because you've got this short exact sequence G tilde to T, right? I want to answer Serre's question for G. I know it for G tilde, but so the punchline is that the norm principle for this map G tilde to T will imply Serre's question for G, right? And it's really a very elementary but beautiful diagram chase. Maybe let me not get into it, but if you're interested, you can give this as some homology exercise. But it's really the norm principle doing the work for you, right? It's really G tilde to T norm principle which kicks in and tells you that G has Serre's question. Okay, so therefore the question really boils down to how do you address the norm principle for maps. And okay, so let me just recap. What is the norm principle question? Is the norm of every image and image, right? You have this incomplete square, and then you start from the left, go to the right, go down. Does it also come from the right? Yeah, so again, this question has been studied independently apart from Serre's question, right? So people already studied norm principle questions, and when do you know, for example, the answer? For example, if G is abelian, right? If G is abelian, then you already have a norm map on this side. So of course the square will commute. So you know norm principle when G is abelian. Again, you have several classical examples. Maybe I can spend some time talking about it. So just like in Serre's question, you have this A, which is a twist of the matrix algebra, and then you have the reduced norm maps from A star to GM, right? And you know Serre's question for this map in the sense that if you have a reduced norm and then you take the norm further, it's also a reduced norm. Okay. And these two are kind of very important for me. So let me just illustrate. So what is the Knebusch norm principle? So this is talking about the spinor norms. So let me talk about it for the quadratic version. So just let's think about the quadratic form as this polynomial equation a1 squared x1 squared plus 1 up to an xn squared. I'm working in characteristic not 2. Okay. What is a value of q? A value of q is simply just any scalar which is not 0 such that it has a solution. Okay. And what are spinor norms? So if you look at all even products, so even number of products of q, of values of q, then this is a group. This is the spinor norm group, and this sits inside the scalars, right? So again, a value of q is simply any non-zero value represented by the quadratic form. Spinor norm, guys, are just you take even number of them, okay, and that is a group, and it's a subgroup of GM, okay, subgroup of K star. You can put it inside. You can sort of classify it as the image as the map from this group, which is called the even Clifford group, to GM. So the image of this map is precisely the spinor norm at every field extension level. Okay, and you know a norm principle here because you prove that the norm of a spinor norm is a spinor norm. Okay, and it's important for me because if Q is even dimensional, this is type D. Okay, so this is one part of type D group. The other part of type D comes from GOQ, right? So you have a quadratic form. This is what is called the group of similitudes. Okay, but so let me put Charlot. I'm sorry for the lights. Okay, so Charlot, and what is a similarity? So similarity is just any scalar such that the quadratic form, when you scale it by the scalar, it's just isometric to Q. Okay, and so the group of similarities. So I think this is called G of Q, and you can realize it as an image from GOQ to GM. Okay. Again, when Q is even dimensional, this is also type D, right? So you have Knebusch on one hand, you have Charlot on the other hand. And I want to mention that this is slightly more general. I mean, this is a different kind of norm principle than these two guys. Okay, why? Because this is a rational variety. So if you think of the underlying variety, the function field is purely transcendental over K. Okay, and this is also a rational variety. It's like it comes from O plus basically, and you have a rational parametrization for it. Whereas this variety is not rational in general. Okay, there are many examples where this is not rational. So in some sense, this is a harder variety to understand. Okay, why am I talking about rationality at this point? Because you have some general norm principle. So this is the work of Philip Gilles and then later by Mercurier, and it says, I mean, they state it more generally, but let me state the rational, let me state the consequence. So supposing you have a G which is rational connected, so as a variety this is rational, right? Then you take any map from G to T, the norm principle just holds for it. Okay, as long as G is rational, you have norm principle. And of course they phrased it more in terms of R equivalence. We have an equivalence relation on every L points level, but let me not get into that. But I want to point out that this recovers Neybush, it doesn't recover Charlot, right? This generalized version of norm principle. This happened in the 90s. So, okay, then maybe 10 years later, so you've got Bhaskhar, Mercurier's result. So Bhaskhar is a student of Mercurier, and they say the following, they prove the following statement, which is, suppose G is connected reductive linear algebraic group, and again they don't want type D components in the Dynkin diagram. Okay, they also don't want E6 or E7. E8 surprisingly is a trivial question in this case, but for classical case you don't want type Dn. So if you remove these extraneous components, then norm principle holds for any map from G to T. Okay, so you see Bhaskhar or Mercurier's result immediately guarantees the Serre's question for us, because for us we just needed G to T, G tilde to T some norm principle map, and you know, if you don't have type D, then this just answers it. Okay, so what is this, right? I can hear you, well, I hope. Say, what about type D and pray, right? So yeah, so let's little longer bear with me as I try to clear the norm principle mystery and tell you what we know. This question is still open though, right? It's been 2 years, but it's still open. So it's a really an intriguing question. So what is mysterious about type D? I mean, why does it not work? Okay, so let me try to now, how do you attack the question of norm principle? I don't want to keep talking about maps from G to an arbitrary torus or a commutative group. So let me do the first elementary reduction. If you have G to T, T is abelian, then it will factor by G mod its commutators. Okay, provided it's defined over the field. But for us, that's the case. And note that this is abelian, so you know norm principle for this portion, okay, already. And so basically, if you know the norm principle for this guy, you already know it for this guy, then you know it for this guy, right? So really the question boils down to saying, do you know the norm principle for the canonical map from G to G mod its commutators? Okay. Once you solve it for this question, then you know the norm principle from G to any map T. Okay, then okay, so now for type D, what is the group which controls the norm principle? It's really, it has a name. Okay, so you take spin, so this is a double cover of O, you take its center, so you have mu sitting inside spin, you embed your center inside this torus, which is called the quasi-trivial torus, where what is Z? Z is just the discriminant of Q. So it's the sign determinant. I mean, the determinant of a quadratic form, you just take the product of the scalars. Discriminant is you sign it appropriately. So okay, whatever. So you have this commutative center, you put it inside this nice quasi-trivial torus, you form what is called the push-out diagram. Okay, and the push-out diagram in this case is basically this cross this mod the diagonal embedding of mu. Okay, and this is what is called the extended Clifford group, omega of Q. And it turns out that the norm principle for this group and twisted versions, I don't just want quadratic forms, but I also want central simple algebras with involutions. But if you solve the norm principle for this guy, then you know norm principle for type T, right? So this is the group of interest, and it has a name, right? It's the extended Clifford group. So people have studied it. Okay, let's do a slight diagram chase. So you have mu sitting inside spin, this sits inside the quasi-trivial torus, this sits inside the extended Clifford group. So then you have this exact sequence. So you have spin inside omega q, and of course you have omega q mod spin to 1. What is this group? What is the semi-simple part of omega q? It's exactly spin q. Okay, so I'm interested in the norm principle map for G to G mod its commutators. So I'm exactly interested in this, in the norm principle for this map. from omega q to omega q mod spin q. Okay, so keeping in mind that, so of course when I try to answer the question for Serre's question, I hit upon this obstruction, right, type D. So I spent some time chasing diagrams and everything, and what I could end up was that, you know, the obstruction to the norm principle lives inside scalars mod the spinor norms, right? So somehow if you're a spinor norm, you produce some, you know, you do a nice diagram chase, you end up with a scalar. If the scalar is a spinor norm, then the norm principle works. If it's not a spinor norm, then you don't know what to do. Actually, if norm principle doesn't work, okay. So really the possible obstructions are in K star mod spinor norms, and then after a point you give up and say, well, maybe it doesn't work because it's not true, right? So can you find a counterexample? And of course, a natural place in this kind of area is to work over completely discrete valued fields, right? So you could try to go up one level and see whether, you know, you have an obstruction there or not. And this is the recent result, and this is the joint work with Chertozov and Merkuriev. So it says the following. So supposing you have a complete discrete valued field, and that's capital K, let the residue field be small k, and assume that small k does not have characteristic 2. Now if the norm principle holds over the residue field, not just over the residue field but also over the finite extensions, right? So if it holds for all quadratic forms at the residue field level and finite extensions, then it holds over the complete discrete valued field case. So if you don't have obstructions over the residue field and finite extensions, you can't produce obstructions over the complete discrete valued field case. So it basically rules out finding a counterexample that easily in some sense. Right, this paper is not just about this result, so it's actually, it has more statements just about norm principles on its own. I'll try to tell you one of them, which is a really cute but very frustrating diagram. So yeah, maybe let me try to tell you one general result from this paper about the norm principle. Okay, so remember that we were interested in the norm principle for this map, right, from omega q to omega q mod spin. If you just complete the diagram a bit, right, its spin mod, its center is the adjoint group. This is omega q mod, this is the center, it's also the adjoint group, right? So it fits into this picture. And you can sort of believe me when I say the norm principle for this question basically becomes a norm principle for the connecting map from PGO plus to H1 mu, okay? And instead of talking about images, you can as well talk about the kernels of this map. So I can sort of restate norm principle as follows. So mu is the center of spin, and then I have this usual map from H1 mu. Let's say I have some field extension L over K to H1 L spin Q. I also have at the K level H1K mu to H1K spin Q. On this side I have a norm map. This is an abelian group, okay? Just like you define norms for K points of algebraic groups, you can also define it for these cohomology groups. You don't have anything here, okay? And now you ask it for the kernels. So if you have an element in the kernel upstairs, so let's call this map say alpha. So if you have something in the kernel of alpha, then is the norm, is it in the kernel at the below level? Right? So the norm principle question translates to this fact here. Is the norm of a kernel a kernel? And here is the nice part. So we define what is called a subgroup HL sitting inside this H1L mu. Okay. So look, we are interested in this kernel of this map. Okay. But this is not a group map. This has no group structure to it. So we sort of want to cut down. I want to look at a group map instead. So you delete some portion of this guy, right? And that's exactly going to be this subgroup HL. So you take a nice subgroup HL sitting inside H1L mu, and this will involve the Charlot norm principle. So it involves the similarities. And then we make sure that this map H1L mu to H1L spin Q, it restricts to a group map from HL and it lands inside not all of this, but it lands inside a group also. It lands inside L star mod spinor norms. Okay, so you start with a subgroup which involves similarities, Charlot. You end up with a subgroup which involves spinor norms, Neighbors, and this is all functorial, right? This is exactly coming from this canonical map here. So you've got h of L to L star mod spin q. You've got h of k to k star mod spin q. Here you have the norm map. Okay, this is because you know the norm principle for Charlot, which is on this side of the board. Okay, I mean you do have a norm map at the abelian, the whole group level, right? But it restricts to a norm map at the subgroup level also, and that is because of Charlot norm principle. Here, of course, L star to K star you have a norm map, but L star mod spinor norms to K star mod spinor norms you have a norm map because you have norm map for Neighbors. Okay, so you have a square, and it combines both Charlot and Neighbors. Okay, and you have a square, but does it commute? Okay, and punchline is that the norm principle holds for that extension exactly when the square commutes. Right, so I've never come across a square which doesn't commute, so we are hoping that this will work, but it's really just the square, right? And we understand this map is just the functorial map here. This is just the usual norm map. You know Charlot, you know Neighbors. So basically, in some meta sense, I guess it means that if Charlot and Neighbors are compatible, right, then this should go through. But it seems like this is like the two ends of the spectrum for type D. And of course, this has many interesting consequences because so it really boils down to making sure this square commutes, right? So in fact, using some nice algebra, you can reduce, you can say, well, you only need to look for L over K quadratic extensions. You don't even need for L over K arbitrary extensions, right? You can sort of do some Galois theory techniques, and you can do a lot of simplifications. But at the end of the day, we still don't know what to do with this. Okay, so I was not able to give you counterexamples. I was not able to give you a definite answer, but maybe I can try to convince you that this is somewhat hard question, probably, because of the following. So maybe take a nice curve over a field and let capital K be its function field. Assume that K is a number field, for example. We realize that this obstruction group basically lived inside this K star mod spinor norms, right? So whatever the problematic scalars lie inside K star mod spinor norms, this sits inside this Galois set, which is H1 K spin Q. Now, because of our result, which says that if you know something for the residue field, you know it for the completions, okay? And because K is a number field, you can in fact show that there are no obstructions over the completions KB, okay? So that is, all these possible obstructions, when you go to KV, they vanish, okay? But if you think about them as living here, so you have guys, probable obstructions which live here, but they're going to vanish when you go to the completions. So it lies in this kernel of this H1K spin Q to H1KV spin Q, okay? Where are the valuations where I take some model, so I'm running over divisorial valuations. But this set has a name, it's called the Tate-Shafarevich set, right? So the possible obstructions to the norm principle live inside this Tate-Shafarevich set. Okay. I mean, of course, so we are trying to, if we manage to show that the norm principle doesn't hold, you would have produced a non-trivial element in the Tate-Shafarevich set. So in general, finding elements here, I'm told, is a very hard question. So probably this is going to be a hard question. So we are not clear yet. I would just like to point out actually that for many fields we know the answer. We know that we know that norm principle holds. So for example, if you take K to be a p-adic field, so like QP, and then so K is going to be the function field in one variable over this, and you have Parimala-Suresh's result which says that the U invariant of K is 8. Okay, so if you take some large enough quadratic form, then it will have, it's going to be isotropic, and then basically it tells you that K star mod spinor norms is trivial for Q dimension at least 9. If you take a 9-dimensional form or more, the obstruction group itself vanishes, right? So there is no obstruction to norm principle. And for lower dimension cases, you have low dimensional isomorphisms with other groups for A, B, C. So you don't have to worry about it. So in this case, there is no obstruction, at least when you think about quadratic forms. Okay, and I think there's a recent result of Suresh where he's if you take small k to be a totally imaginary number field. Of course, we don't know about the U invariant yet, but I believe that this is true. This group is anyway going to be trivial. Okay, when you take k to be a totally imaginary number field and you take capital K to be the function field in one variable over it, again this group vanishes. And so maybe a possible thing would be to look at guys with real places and see if you hit upon some obstructions. But it's sort of more and more evidence that maybe norm principle just holds, but it's a give or take question. Okay. Okay, so just to complete, go back to Serre's question. Of course, I stated it as saying you have this result, at least in the classical case, for type A, B, and C. But I just want to point out that if norm principle holds for type D, then it also holds. Serre's question is also answered. The proof just follows through. But I mean, because the norm principle seems a harder question, so you might ask, well, can you attack Serre's question without norm principle? Is there a chance? I just want to point out that you have this exact sequence, right? I wanted the answer for G, and I said if norm principle holds for G tilde to T, then it holds for G. But it's a diagram chase, right? So you can sort of go back, and it turns out that Serre's question for G will imply not the whole norm principle, but it will involve what is called a weak norm principle for G tilde to T. Okay, but it's very hard to get hands on this weak norm principle. So either you end up proving the strong norm principle or you don't have anything at all. So this seems a very hard question to tackle, just the weak norm principle. But anyway, it seems like it's somewhat necessary. You see, said the tortoise. I see, said Achilles, and then there was a touch of sadness in his tone. So maybe I will stop with that. Thank you.
Any questions?
There's no other question. I have a somewhat silly question. So in your slide where your D, you had some adjective before that.
Which one?
Classical types A, B, C, and then something B. Try something.
Non-trilitarian. So you have this is the exceptional group. So you have this Dinkit diagram for type D, right? And in this case you have this extra. Yeah. So that is the exceptional group. Yeah.
Any common question? I have a question.
Yes.
What about nilpotent groups and soluble groups?
We have.
So there was some exact sequence where you had abelian by something and then.
Right.
But you assume something about the.
All the groups are basically going to be a smooth for us, and we don't have a reduced. We don't have. I'm sorry. Are you talking about the group scheme structure or?
No, just.
Oh, just for like solvable groups.
Yeah, solvable groups instead of semi-simple.
Oh, okay.
You almost have it in some way, but there was some extension of something by abelian, and then, but you made some assumption about the kernel quasi something. I forgot what you said.
Actually, I've not thought about the question for solvable groups, but I believe maybe.
Yeah. So the next slide. So that is the exact sequence. So maybe previous one. Here.
Right.
So A, if Serre's question holds for A.
Right. I think we should be able to get it for solvable. Maybe just these ones. Yeah. I will double check and get back to you if I'm missing something, but that might be true. Yeah. It should be phone. Yeah. But I don't know what if you have GA and all. I mean. Yeah. More, yeah. Nilpotent one, yeah.
And this curve you always assume
Smooth.
I mean, are you working with affine space or no?
No, this here it will be a projective curve. Here it will be a projective. Yeah. Here it will be a projective curve. Yeah.
Anyway, you are looking at only the function.
Only the function field. Yeah.
So what type of curve? Okay, it's assumed smooth.
So I just need like a nice model for the curve.
You are not. I'm just only asking whether you are assuming k to be actually k round bracket t. You are not assuming that.
No. It's any function field. Any function field in one variable. Transition degree 1. Correct. Yeah.